Hello students, welcome to Sri Jayendra's Ring Zone classes. I'm your friend and mentor for coming classes with respect to physics. This is lecture number 1 of our unit, atoms. So let's begin with the atoms. In today's session, first we are going to discuss about the alpha particle scattering and Rutherford's nuclear model of an atom. So let's begin with the alpha particle scattering experiment by the Rutherford. What the experiment is that Rutherford performs an experiment on the scattering of an alpha particle by using extremely thin gold foil and made the following observations. As you can see this, that this is the source of the alpha particles and this is a very thin gold foil, and is this is the circular fluorescent screen. So when an alpha particle passes or developing from this source, it is going to collide, it is going to pass through this thin gold foil, and with this thin gold foil, from this thin gold foil, a certain scattering of an element, a certain scattering will happen, and that has been received on circular fluorescent screen, and that observation is being calculated and is being noted, and then he came to the conclusion. So he concluded that most of the alpha particles passes through the foil straight away, that means undeflected, while some of them are deflected through very small angles. So when we talk about the numbers, we can say that only about 0.14 percentage of the incident alpha particles scattered by more than 1 degree. So it is a very less number that has been scattered, or I should say about 1 in approximately 8,000 deflect by more than 90 degree. So he has given us a number, that the number of scattered particle in a particular direction with respect to theta, that could be given as this n is directly proportional to the 1 by sine to the power 4 theta by 2, where theta is the scattering angle. So basically it gives the number of particles that has been deflected by certain angle. I hope this is clear. Please note it down. It's an n of theta inversely proportional to the fourth power of sine theta by 2. I hope this is clear. Now let's discuss about the another important parameter, that is the distance of closest approach. It's a nuclear dimensions. So what the situation is that let's suppose this is the minimum distance from the center of the nucleus up to which the alpha particle approaches is known as the distance of closest approach. From the figure, this is clear that let's suppose at this point a particle is at infinitely away, and as it is at infinitely away, it is having a total energy. While I say it's a total energy, I mean it's a potential energy plus kinetic energy. But potential energy at infinite is defined as a zero, so it is having only the kinetic energy, and that kinetic energy would be equals to half mv square. When it is moving in this direction, it is the location of, let's say, a center nucleus, and this is the r minimum. So at this point, if you see this, at this point, let me show you. This is the location. At this point, this particle is coming to the rest, and if it is coming to the rest, it is having potential energy plus kinetic energy, within which kinetic energy, it is zero. And if kinetic energy is zero, only potential energy will remain. That potential energy would be k into q1 multiplied by q2 divided by r. Now let's suppose I represent this q2 by z into e and q1 as an e. So this is equals to k into z e square divided by r. So if I'm going to compare this, that half mv square is equals to k z e square by r, then I will have this r naught is equals to 1 upon 4 pi epsilon naught z e square by k e. It's a kinetic energy. So this is kinetic energy is equals to half mv square. I hope this is clear. So you can understood that your electron or your bombarded element never reaches to the center of the nucleus. It has reached a very close to the center of the nucleus, but it we cannot assume that, or we cannot consider that it is going to hit this element and it is going to rebound from that. No, it is not going to hit that. This is simply not possible. I hope this is clear. So please keep this in mind. A very good concept. It's a distance of closest approach. Now let's discuss impact parameter, another very important aspect of Rutherford's experiment. He said that it is the perpendicular distance of the velocity vector v of the alpha particles from the center of the nucleus when it is far away from the nucleus is known as the impact parameter. So let's understand that this is the nucleus and this is its center. My alpha particle has been started moving in this direction. So if I take a perpendicular distance of these two lines, because it is at the center of the nucleus, this is what we call as an impact parameter. It is that perpendicular distance that we call as an impact parameter, as I have seen this in the diagram also. So this is the trajectory of a particle and this is the nucleus. Now due to a force of repulsion, because this electron having a negatively charged, this nucleus having the negative charges, yes, it's a Z into E basically. So from this due to this particle has traveled in this direction and then it has been shifted to this. So there is a certain angle with which it has scattered. Yes, so that angle and the formula between this impact parameter b and this angle could be given as it is b, that is equals to, this is b is equals to 1 upon 4 pi epsilon naught. It's a z e square cot theta by 2 upon half mv square. Or if you want only the relation with the angle, then it is b which is directly proportional to the, it is a b which is directly proportional to the cot theta by 2. Now in this relation the z, it's an atomic number, e, it's a charge of an electron, theta, it's a scattering angle, m, mass of alpha particle, and v, velocity of alpha particle. I hope all this are clear. Is it clear? Is it clear? Great. Let's have some of the questions based on this theories. That it says that if x number of particles, if x number of particles has been scattered by an angle of 90 degree and y number of particles has been scattered by an angle of 60 degree, then find ratio of x to the y. This is the question. How will I do this? He says that if x number of particles has been scattered by an angle of 90 degree and y number of particles has been scattered by an angle of 60 degree, then find out the ratio of x is to y. So the situation is it's an n of theta directly proportional to the 1 by sine to the power 4 theta by 2. I hope this is clear. So this is n of theta is inversely proportional to the fourth power of sine theta by 2. Now from this let's take a directly ratio. It's an x to the y. This is equals to sine to the power 4 power of theta by 2. X is the number and angle was the 90 degree. It's a 90 by 2 which is 45 degree. And y is the number when particle has been scattered by an angle of 60 degree. It's a sine to the power 4 30 degree. So when I say sine 30 degree, it's a 1 by 2. Sine 30, it's a 1 by 2 to the power 4. And it's a sine 45, it's a 1 by root 2 to the power 4. So this is 1 by 2 to the power 4, which is a 1 by 16 multiplied by. It's a 1 by root 2. It's a root 2, root 2, root 2, root 2. This is 4 is to 1. So this is equals to 1 is to 4. This is equals to x by y. I hope this is clear. Is it clear? Is it? Are you sure? Do you have any doubts up till now? Is there anything? Do you have anything? Do you have any doubts? Is there anything? No? Great. Let's do it for the impact parameter. The question says that if scattering angle is 90 degree, then impact parameter is of, let's say, x. If scattering angle is decreased by 30 degree, then impact parameter should be y. Find ratio of x is to y. This is requirement. How will I do this? So according to the standard relations, it should be a impact parameter is proportional to the cot theta by 2, and when it is proportional to the cot theta by 2, initially it was at 90 degree, and impact parameter is of x, so this is x directly proportional to the cot 90 by 2, which is equals to cot 45 degree. And now impact parameter is y, when this is equals to, let me remove the proportionality symbol and directly take a ratio. It is a cot of, it has been decreased by 30 degrees, so it was initially 90, now it has been decreased by 30, so that is be equals to 90 minus 30, which is equals to 60. But what I want a theta by 2, it's a cot of 30 degree. I hope this is clear. So cot 45, it's a 1, and cot 30, what it is, yes, tan 30, 1 by root 3. Cot 30, it's a root 3, so this is equals to 1 is to root 3. I hope this is clear. Is it clear? Any doubts? Is there anything? Is there? No? Great. So let's look at the all the conclusions that Rutherford has made after his experiments. He said that most of the mass and all the positive charges of an atom is concentrated in a very small region that we call as an atomic nucleus. Second, we see that nucleus is a positively charged, and its size is of the order of 10 to the power minus of 15 meter. And most of the space in an atom is empty, and electrons revolve around the nucleus like planets revolve around the sun. So relations of the motion of the planets around the sun and the relations of the electrons moving around the atoms could be somehow similar. So do you understand up till this? Do you understand this? Are you sure? Great. Now let's discuss certain drawbacks that we could not answer certainly. That first is the stability of an atom. It says that it could not explain stability of an atom because according to the classical electrodynamics theory, an accelerated an accelerated charge particle should continuously radiate energy. But if it is going to radiate energy, it is collapse. How? Let's look. So if an electron moving in a circular path around the nucleus should also radiates the energy, and so he should move into smaller and smaller orbits of gradually decreasing radius, and it should ultimately fall into nucleus. Now, this is not the situation. We have never seen that an electron is there and it is radiating energy and it is going to decrease its radius, and at a certain time it is going to collide with the nucleus or with the central part, and it is going to be collapse. We have never seen this. According to this model, the spectrum of atom must be continuous, whereas what we receive is a line spectrum. So it did not explain the distribution of electrons outside the nucleus, that how electrons is being distributed outside the nucleus. He does not tell us. I hope this is clear. These are the limitations of this model. But let's look at these certain quick questions. Be ready with it. It says that impact parameter is the blank distance of the initial velocity vector of the alpha particle from the center of the nucleus. Yes, the impact parameter is the perpendicular. It is the perpendicular distance of the initial velocity vector of the alpha particle from the center of the nucleus. Next, a 1 Fermi. Yes, 1 Fermi. It's a 10 to the power minus of 15 meter. Next, a relation between distance of closest approach and kinetic energy of the alpha particle. At that time we have derived, but let's derive it one more time. Let's suppose this is the particle. This is the, let's say, a particle having at infinite distance having kinetic energy. Let's say this is the nucleus, this is its center. As it is moving in this direction, at certain instant of time let's suppose situation is something like this, that it has reached to this, and at this position it is at rest. So this is the distance of closest approach that we call as an r. Here it is having a kinetic energy, and at this point this is, let's say, location 1, and this is location 2. So it is total energy at 1, that should be is equals to total energy at 2. In At this situation it is having half mv square plus 0, because potential energy is 0 at the infinite location, is equals to, here it's a potential energy, it's a k multiplied by q1 multiplied by q2 divided by r plus half mv square, but that would be equals to 0 because it is at rest. So this is, from this location, r is equals to k q1 q2 divide by half mv square. This is distance of closest approach. Higher the energy, lowest or the least would be the distance of closest approach, but this could not be a 0. I hope this is clear. So this distance of closest approach is inversely proportional to the kinetic energy. I hope this is clear. Is it clear? Great. Now next, it's a relation between the impact parameter and scattering angle, that is be directly proportional to the cot theta by 2. I hope this is clear. So do you have any doubts? Is there anything? No? Great. Now let's discuss the Bohr's model of the hydrogen atom. We have seen the atomic model or the atomic conclusions that has been done by the Rutherford from this alpha particle scattering experiment. So he has certainly answer certain questions that a central element would be there, and that element would be a positively charged particle, and all the electrons are there, they will be distributed like an cloud like of environment. But he has a very loopholes that how this will be. He could not answer many of the questions, so we will try to find out. We will try to find out those answers from the next model, that is of Bohr's model. So let's have a look. To to understand the model, first he gave a certain postulates. So let's see. A Bohr is combining classical and quantum concepts, and he gave his theory in the form of the three postulates. Now, first thing, what do you understand by postulates? What is it? When I say it's a postulates, that means we are going to accept it. We are going to accept it, and we can investigate by considering that this assumption is correct. But when and when we derive, or when we say this is postulate, we already have a proof of it. While I say proof of it, I mean we are having a verification of it. I could not say, maybe proof is probably a different word, but we could verify it. And once it has been passed through the many or verifications, many observations, then they have been received it as a postulate. I hope this is clear. So whatever the postulates are, you are going to consider it that this are correct, and from that we are going to derive in a next phase. Yes. So let's look at the first postulate. He says that an electron in an atom could revolve in certain stable orbits without the emission of radiant energy, and this orbits are called as the stationary orbits. Yes. And so when an electron is there, it is revolving in a certain stable orbits only. And when it is moving, or it is revolving in that certain stable orbits, it is not going to radiate any energy. That was the theory. They said that it does not define the stability of an electron. He has an answer of this. Now let's look at the second. He said that electron revolves around the nucleus only in those orbits for which the angular momentum is some integral multiple of h by 2 pi, where h is the Planck's constant. So he said that when or in whatever orbit it is going to revolve, that orbit must be having an angular momentum of integral multiple of h by 2 pi, where n is equals to 1, 2, 3 and onwards, and this n is known as the principal quantum number. So it can revolve is only in certain stable orbits only, and that certain stable orbits will satisfy this rule. It's an L is equals to ns by 2 pi. This was the second postulate. Let's move forward to the third postulate. He said that an electron might make a transition from one of its specified non-radiating orbits to another of lower energy, and when it does so, a photon is emitted having energy equal to the energy difference between the initial and the final states. So basically the situation would be something like this, as you have understand and learn this in chemistry too. So but let's revise it one more time. Let's suppose this is the energy level 1, it's an E1. This is the energy level E2, and let's suppose a certain electron is there. He has received a certain amount of energy from certain sort of sources. So if it received the energy, what the situation will be, that after receiving this energy, this electron will jump to this orbital state. It's an E2, and we could say that E2 is greater than E1 energy wise. So when it has been shifted itself to the next energy level, which is E2. This electron is not at all stable here, so he has not received any stability over here. So what situation will, that as it is not stable at here, so this electron will jump back to this situation. But if you want to, if you want to switch it back, if you want to jump it back from E2 to E1, what the situation will be, you need to develop one of the photon, and that photon will be having an energy which is equals to HF, which HF should be equals to energy of the final level minus energy of the initial level. I hope this is clear. So this would be the situation. He said this, that when electron make a transit, it is not it is not compulsory to transit. It might possible that electron will transit from one of its energy level to the another energy level. It should radiate a certain photons, but for this it is going to transit itself from a higher orbital state or higher energy states to lower energy state. That is for sure. I hope this is clear. So these are the three postulates that Bohr has considered, that this all are the true. This all has been verified, and we can use the conclusion of this relations. We can use the conclusion of this relations, and we will derive whatever we want to. I hope this is clear. So from this Bohr came to the mathematical modeling of this motion. So what he has done is that he has considered that, let's suppose this is a central element, and that central element, let's call its a charge as a Ze, and an electron is revolving around its nucleus. So basically this is the radius r of its motion. So he has derived first the radius, then the velocity, then the time period and everything. But whatever Bohr has given, it is not for the ZE. Or I should say, if I write it's a ZE, then it would be a Z equals to 1. It is for Bohr's model. But I have derived it according to the Z, because same amount, same model, same mathematical modeling, same formulas can be applied to different elements too, provided this Z will be changes. That means if they said that lithium will behave like this, find out its radius or find out its velocity, then I will put Z is equals to 3. If they said alpha particle is behaving like this, then I will put alpha Z of the alpha particle, or I should say Z of the helium particle, sorry. If they said a sodium will behave like this, I will put Z is equals to 11. I hope this is clear. So I basically Bohr has derived for the hydrogen, and if he is deriving it, he will put H is equals to 1. I have derived it generalized terms so that we can have a questions of all the situations. So he said that, let's begin with the radius of the Bohr orbit. It's a for an electron revolving around a stationary nucleus. The electrostatic force of attraction provides the necessary centripetal acceleration, and this necessary centripetal force or this necessary centripetal acceleration could be given as, it is equals to F electrostatic, that is equals to mv square divided by r. This F could be written as it's a k into q1 into q2 divided by r square. That would be equals to mv square by r. This was the first relation, keep this in mind. And and second relation, that angular momentum mvr, that would be equals to nh by 2 pi. This is the second relation. So from this above two equations I can have the radius of nth orbit, which is given as this Rn, which is equals to n square h square upon 4 pi square kz me square. And from this It is something like this r square is equals to, keep this n square aside, keep this z aside, and if I calculate all this stuff, this is equals to 0.53 Armstrong multiplied by n square by z. So this radius of the orbit is directly proportional to the square of the orbital number, divide by it's an atomic number, n square by z. Thus radius of innermost orbit n equals to 1 of the hydrogen atom, where z is equals to 1, is called Bohr's radius, that we call as an r naught, which is equals to 0.53 Armstrong. One more thing, when I say n, it's an orbital number, or we said say it's a principal quantum number. So when I say it's a ground state, when we say it's a ground state, then it will be n equals to 1. If it's a second state, it's a second orbit, it's a second orbit, you will say n equals to 2. If I say if i say that it is third excited orbit, when word excited is there, you need to add something, you need to add one more. So it's a third excited, so it would be n equals to 3 plus 1 is equals to 4. I hope this is clear to you. Is it is it clear? Great. Now let's work for the speed of an electron. So from the above relations we have relations this 1 and 2, and from this here we are having the mv square by r as well. So from this I can derive the speed of the electron in nth orbit, that can be calculated as, this is equals to v is equals to z square upon 2 epsilon naught n into h. So if I keep aside a z and n, if I keep aside a z and n, this will equals to a c by 137, or 2.2 into 10 to the power 6 multiplied by z by n, where z is the, what it is, yes, z is the atomic number, and n, it's a principal quantum number. N is the principal quantum number. So this will be the situation. This is equals to c by 137, or it's a 2.2 into 10 to the power 6. I hope this is clear. Now the ratio of the speed of an electron in the ground state in Bohr's first orbit of hydrogen atom to velocity of light in air is equals to, it's an e square divided by 2 epsilon naught into ch, where c is the speed of the light in air. So please keep this in mind, as well as noted it down, that what is v, what is r. Yes, we required a last formula, we only required a last formula, and this is only the requirement, but you need to remember this. Next, it's an angular frequency, omega, omega of an electron in the nth orbit. If I derived the omega of an electron, then it's an omega n, that would be equals to omega naught, where omega naught is equals to this constant multiplied by z square by n cube, where omega naught is the angular frequency of electron. It is the angular frequency of electron in the first Bohr's orbit of hydrogen atom, and that could be given as 4.459 into 10 to the power 6. That is the value, this is the value of omega naught multiplied by z square by n cube radian per second. I hope this is clear. Is it clear? Is it clear? From this omega you can have a frequency too, it is from 2 pi f. Yes. So this is the situation. Next period of revolution of electron in the nth orbit. I am having the radius, I am having the velocity, so from this time period can be calculated very easily. This time period would be equals to 2 pi r divided by v, and from this if I put up the value, it will look like this. So if I keep this n cube aside, this z square aside, all the other terms that we call as a constant. This is Tn is equals to T naught into bracket n cube divided by z square. And from this T naught it is 1.51 into 10 to the power minus of 16, which is equals multiplied by n cube by z square. I hope this is clear. Is it clear? Is it? Are you sure? Great. Let's look at the electric current. Electric current due to electron motion in nth orbit. It's in current. So basically this has been derived from the fact that it is the relation of z square by n cube into m, while this m this m is the magnetic moment. We have studied all this. Yes, it's a magnetic moment of the electron in the nth orbit, and that m could be given as m is equals to I into a. Have you noted it? Great. Let's look at this last. It's a total energy. It's a total energy of electron in the nth orbit. So this total energy En is equals to potential energy plus kinetic energy, and that would be is equals to minus of k into z square divided by 2Rn. So from this, if I replace the value, the total energy I received, it's R into Ch into z square divided by n square, where R is the Rydberg's constant, and its value would be 1.03 into 10 to the power 7 meter inverse. So the total energy would be minus of 13.6. It's a minus of 13.6 into z square divided by n square in electron volts. I hope this is clear. Is it clear up till now? Now, do you have any doubts, any confusion up till now? Do you? Do you have anything? Do you have any doubts? Are you sure? Great. So, shall we summarize this? Shall we summarize this whole relations? It's a first, which is equals to radius of orbit. What was it? Radius of orbit. It is r, which is directly proportional to the n square by z. Second, sorry, it's a radius of an electron. It's a radius of electron. Next, it's a velocity, which is equals to v directly proportional to the it's a z by n. Next, it's a time period of revolution. So this t directly proportional to the this t is directly proportional to the what it is. Yes, it's an n cube by z square. Frequency, that's a fourth. Let's say a frequency of revolution. This f directly proportional to the z square by n cube. Next, energy. This total energy E is equals to minus of that we say it minus of 13.6 into z square by n square. So at least you should keep this all into your mind, as well as you must know the constant of this. You must know the constant of this. So do you know what is constant of this? It's an R naught. What would be its value? If I replace this proportionality symbol, we are aware that there is a certain number over there. What it is? What was that number? What was that R naught? Yes, it is approximately 0.53 Armstrong. Okay, great. If I remove here proportionality symbol, then what is V naught? It would be a C by 137, or it would be a 2.2 into 10 to the power 6. It's a 2.2 into 10 to the power 6 meter per second. Now if I remove this proportionality symbol from here, then it's a time period. This time period could be given as what it is. It's a this time period. It would be a 1.51 into 10 to the power minus of 16 seconds. For this frequency, it is just inverse of 1 by t naught. And here I have already written it. So please keep this in mind, as well as please noted it down. Please noted it down in your book as well. Please noted it down. Have you noted it? Have you? Have you noted it down? Are you sure? Have you did it? Great. So now ready for the question? Are you? Are you ready for the question? Let's have a look. The question says that find out ratio of radius, velocity, time period, frequency, and energy for for electron moving in the second orbit to the second excited orbit around hydrogen atom. So this is the question. How will you deal with this? What is to be done? So he said that you need to find out the ratio of the radius, velocity, time period, frequency, and energy for the electron moving in the second orbit. So let's call this n1 as a 2, and to the second excited orbit. So this n2, this will be 3 for the hydrogen atom. So this is n1 equals to 2 and n2 is equals to 3. So from this I can have the value as this is r1 is to r2. This is equals to n this is equals to r is directly proportional to the n square z, but here both are revolving around the hydrogen atom only, so this is equals to n1 square divide by n2 square. So this is equals to 2 is to 3, so it's a square of them, it's a 4 is to 9. This is the radius, or this is the ratio of the radius, sorry. Now let's take the case of the velocity. It's a v1 is to v2, and v1 is to v2, that is what we call as a z by n. So from this it's a 1 by n1 to the 1 by n2. So basically it is just the ratio of n2 is to n1, and if it is n2 is to n1, it's a 3 is to 2. So this is the ratio of their velocity. Now let's work for the time period. So for the time period, this t is directly proportional to the n cube by z square. So here it's a t1 by t2, it is equals to n1 cube by n2 cube. And if it is an n1 cube by n2 cube, this is equals to 2 to the power 3, it's an 8. Divided by 3 to the power 3, it's a 27. So this t1 is to t2. This is equals to 8 by 27. This is time period. Next, it's a frequency. So if I write a frequency over here only, it is just the inverse of this. It's a 27 is to 8. Did it. Next, energy. Yes, it's an energy of the electron. So if I find out the energy, then this is the standard formula of energy. It's a minus of 13.6 multiplied by z square divided by n square. Here z is equals to 1 because it is an hydrogen atom. This is equals to E1 is to E2. This is equals to minus of 13.6 multiplied by this is n1 square multiplied by minus of 13.6 into n2 square. This 2 has gone. This is equals to n2 square divided by n1 square. N2, it's a 3, so this is 9 is to 4. This is the ratio of the E1 is to E2. I hope this is clear. Is it clear? Is it? Are you sure? Are you sure? Great. Now I want to derive one more thing, that it is the relation for magnetic field. Relation for magnetic field at the center when electron is revolving around the atom. So as I know that if it is the situation that this is the center element, let's call it ZE, and this is the electron which is revolving around this, then it will produce a magnetic field, and that magnetic field could be calculated as mu naught I by 2r. So basically what I understand is this B is directly proportional to the I by R. Now how could I write I? That is equals to Q by T. And how could I write T? It's a 2 pi R by V. So basically this would be the situation. So from this it is B is equals to mu naught by 2. Keep it aside. I I that would be equals to QV by 2 pi R. This is multiplied by 1 by R. So this basically a magnetic field is directly proportional to the V by R square. Now as I know that V is directly proportional to the Z by N, and R is directly proportional to the N square by Z. R is directly proportional to the N square by Z. So this is equals to N to the power 4 into Z square. I hope this is clear. So this will give me a Z cube divided by N to the power 5. This is the magnetic field at the center. Yes. So shall I continue the previous question? In the previous question, in the previous question, find out ratio of magnetic fields at their centers. So how will you do it? It's a B1 is to B2, that is equals to N1 to the power 5, and this is N2 to the power 5. Now I am having the relation which is equals to N1 is equals to 2 and N2 is equals to 3. So it's an N1 equals to 2 and N2 equals to 3. So this will be, it's a 3 to the power 5 divided by 2 to the power 5. It is something like this. When I say 3 to the power 4, 3 to the power 4, it's an 81 into 3, because it's a 3 to the power 5, it's a 2 to the power 5, it's a 32. So 81 3s, it's a 243 divided by 32. This is the ratio. I hope this is clear. Is it clear? Are you sure? Are you sure? Do you have any doubts up till now? Do you have anything? Any doubts? Is there anything? Is there anything? No? Great. So ready for the next question? Let's have a look. The question says that what should be the ratio of product of velocity and time period velocity and time period of electron orbiting in in third and fourth excited orbits around hydrogen atom. So go through the question and let me know what is to be done and how this can be achieved. So what they say it is that what should be the ratio of product. First I need to find out this. It's a product of velocity and time. When I say it's a product of velocity and time, first velocity, it is directly proportional to the z by n, and then time period. This time period was equals to t directly proportional to the n cube by z square. So if I multiply this, this is equals to v into t, which is proportional to the, it's a z by n multiplied by n cube by z square. So this is proportional to the, it's an n cube, which is equals to n square. Divide by, this is z square, it's a z. So this v into t is equals to n square by z. This is v into t. So what I need to do, let's calculate it, because both are moving in the hydrogen atom, around the hydrogen atom. So it would be a z is equals to 1. So it's a v into t of the first orbit divided by v into t of the next orbit. Yes, it's an n square, it says n1 square by n2 square. So they are moving in the third orbit, so let's call it n1 equals to 3, and it's a fourth excited orbit, so it's an n2 would be equals to 4 plus 1, which is equals to 5. So this is equals to 3 square divide by 5 square. This is 9 is to 25. I hope this is clear, and you can certainly do this kind of questions. Yes, so let's look at certain quick questions. The question says that the electron can revolve only in certain discrete non-radiation orbits that we call as in, yes, they are the stationary orbits. And which all orbits are there? Let's look at the second question. It says that the total angular momentum of the revolving electron is an integral multiple of, yes, h by 2 pi. Next, it's an electric current due to electron motion in nth orbit is directly proportional to the z square by n cube. This I is directly proportional to the z square by n cube. I hope this is clear. Is it clear up till now? Is there any doubts? Is there? Is there any doubts? Anything? No? So let's wind it up this session over here. In this session we have started it with the Rutherford's atomic model, and then we have switched to the Bohr's atomic model, and we have done that how, what should be the radius, or what should be the velocity, or what should be the total energy and everything. Yes, so please revise this lecture, and please remember all those formulas that we have derived. We must understood and we must remember the relation with atomic number z and principal quantum number n. Please do this. This is very important aspect, and this is the modern physics which is covering a large portion of our competitive examinations. So please go through this, please revise this. This will help us. Definitely this will help us to get the good numbers. Thank you. Have a good day. Take care. Bye bye.